Hello, everyone. Welcome to This Week on Mars. My name is Ian Hewitt with the Gupta College of Science here at Coastal Carolina University. And this week we're going to be talking about sound on Mars. That's the latest news that's released from NASA, and we'll be delving into it. First, we should probably talk just a little bit about what sound is, right? We all experience sound every day. If you've got a puppy near you and it starts barking, you hear the barking, and that's actually sound waves. So the action of the puppy of barking is actually pushing the air and making sound waves that kind of go out in a circle from the puppy's head, and it goes to your ear, and you hear it. Depending on the puppy, maybe kind of quiet. Or it may be really, really loud. Some dogs are really loud. It may be very low pitched, or it may be very high pitched. So I know I don't do a good bark sound, but it may be different and depending on the puppy. So what actually is happening with sound waves? And in order to understand what we're hearing on Mars, you probably need to understand a little bit about sound. So we'll just talk a little bit about that, about sound in general, and then we can go on to sound on Mars. So what happens when you make sounds? Well, when you actually make sounds here on Earth, and it doesn't matter any type of sound, whether it's the sound of you dropping something, whether it's the sound of you talking, or whether it's the sound of you breathing, or whether you hear a car or a fire truck go by, it's all the same. What happens is the action of whatever device is making the sound. Maybe it's a speaker. You're listening to me right now. Maybe you've got headphones like I do. The headphones will have a speaker in there. And what a speaker actually does is if you ever put your hand on a speaker, you can kind of feel it. And what it does is it actually vibrates back and forth a little bit. And what that vibration is doing is it's actually pushing on the air molecules. So what it does is it actually, when it pushes out, it kind of scrunches some of the air molecules together. And then behind that, when it kind of pulls back, it kind of stretches out the molecules. So they're no longer evenly distributed. You'll have a little zone where there's a lot of air molecules packed together, and you'll have a zone behind it where there isn't. And what happens is it does this very quickly, and basically you'll create basically this set of areas where you've got molecules pushed together. And I'll actually draw a little picture here. You've got molecules. You've got areas where molecules are pushed together, and right, were these three areas dark areas? And you've got areas where they're far apart. Now, you may think when you first look at this that, like, when you're hearing a dog bark or you're hearing my voice, that this would be one complete bark, this packed in area. And that's actually not what's happening. What's happening is that you actually, when you get a sound, you're actually getting a whole bunch of these packed areas and areas where there's less packing, right? So you're actually getting a whole series of them and you're getting multiples of those every second. How many of those you get, how tightly packed these dense areas are, how many there are in any given time, is the frequency. It's whether it sounds high or sounds low. If there's a lot of them packed together, it's a high frequency and it's going to be a very high pitched sound. If there is fewer of the packed areas at a given time, it's going to be a low frequency sound. Now, humans are real good at hearing a wide range of frequencies, but we don't hear all of them. You hear ultrasound or like a dog whistle. To go back to dogs, and when a dog whistle blows, it actually emits at a higher frequency than people can hear, but a dog can certainly hear it because their ears are better than ours. So all this kind of makes up a sound wave. When you look at it, when you look at these packed areas, you look at it has a sound wave. And the wavelength is just the distance between various crests and peak. And that's wavelength is like frequency, except wavelength changes. Wavelength gets longer as frequency gets lower. So it's kind of the opposite of frequency, but it's just a different way of saying the pitch of whether it sounds high or low. So when you get this effect, um, in just a completely homogeneous mass of air, when you make a noise like you bark or you talk, your sound waves go out in kind of a circle, ever expanding circle from the source. Just like your speaker and your headphones, or if you're listening to speaker on your desktop, it'll the sound waves will go out in an expanding sphere, which is why it's not just pointed straight at you. Anybody else in the room can hear it, but it is a little bit weaker if you're standing right behind the speaker. That's kind of why that happens. But the thing is, if the air is not quite the same in different parts, it will affect how the sound travels in the air. For example, cooler air, sound waves travel a little bit slower, and warmer air they travel faster. Same thing will also occur when you start changing the pressure, which we'll talk about on Mars, because their atmospheric pressure is different than ours. But what you get is this is one of the reasons you get some weird effects with sound. For example, there's something if you live near a lake, or if you've ever been near a lake, or you've been near the ocean, a lot of people always say, well, sound travels better over the water. And that's true. And why is that? Well, the reason is that the water tends to always be cooler than the air. In fact, that's almost always true everywhere you are. So sound is going to travel a little slower in the cool air near the water's surface. So down here near the surface is going to travel slower. But as you go up, the air is going to be warmer. So the sound is going to travel faster in warmer air. So the net effect is that instead of having that sphere, the top part of those sound waves will kind of straighten out and it'll be a solid wall of sound. Much easier to hear, much more coherent. And that's why sound travels faster over water. So now we'll talk a little bit about how that affects Mars. You may be saying to yourself, well, this is supposed to be about Mars. So why are we talking about all these sound related things? Well, let's talk about Mars. So one thing the Perseverance rover has that's fairly new on Mars is it actually has a pair of microphones. Now, there actually have been two other microphones, or one other microphone sent to Mars, but unfortunately that didn't return any results. So this one, but Perseverance has two. So you can see it's got one down here on the body. This was for the entry, descent, and landing. That's this circle here on the right hand side of the screen, and right here, and then it's got one on the mast cam, which the mast is this part that sticks up that has the camera and the laser on it. We'll talk a lot more about the laser in a different video, but you can see it's got a microphone up here, and this is the one we're really interested in. This particular microphone right here. This is actually a first because it's actually meant to record a broad range of sound on Mars. It's really, really super helpful. Why would you do that? So why would we want that, right? Okay, you always have a limited amount of equipment you can carry to Mars. So why would you want sound? I mean, what could you learn from that? Well, you can actually learn quite a bit because sound gives you an additional sense and lets you pick up things that you may not pick up otherwise. The rover has lots of cameras, so it's got sight. It doesn't really have a feel. Kind of a feel. You can almost say it has taste, a sense of taste, because it has the onboard chemical laboratory, so it can actually check out, basically sample different things and get a feel for them. But sound gives you another sense, and there's a couple reasons you want to do that. The first of all is what they call an engineering reason. And one of the things about engineering is there's a whole team that's designed to keep this rover running. We want to keep this rover running for 10, 15 years ideally, and keep returning results. Well, that requires constant checkups on whether things are running correctly. The camera on the end of the arm, at the end of the robotic arm here, is able to go and come up and take pictures all around the rover. So the engineers at NASA and JPL can actually look at the rover and make sure things are functioning properly. But that doesn't always give you the same story. For example, maybe something is not, maybe there's a bearing is clogged with dust, and you might not be able to see that with a camera. But having a microphone, you may be able to hear if something's squealing or grinding, and you may be able to address the problem or work around it before it becomes something serious and something breaks. Because if something breaks on Mars, well, it's sort of game over because you can't really go out and fix it and can't click reset, and we don't get extra lives on Mars or any special power-ups. We basically have to go with what we have. But the other reason is it's used for science purposes. Again, the Mastcam has a laser. And one of the things is we'll talk a lot about the laser in another video, but when it hits something, it makes a noise just like you would expect. And that noise can tell you something. When you analyze the sound waves coming out of that noise, it can tell you about the object it's shooting at. It can tell you about its mass. It can tell you about its composition. Basically, the sound when the laser hits it makes a big difference. So it adds a whole new dimension to analyzing data on Mars. Okay, so what would it sound like if you were on Mars? Well, there's actually a really cool site that NASA put up basically this week called Sounds of Mars, and this is the link. We'll see if I can put this in the comments. MarsNasa.gov, Mars 2020 Participate Sounds, and it lets you record a quick soundbite or a quick greeting, and then it would play it back how it sounds on Mars. Okay, why wouldn't it sound the same? Well, the thing is, Mars does have an atmosphere, but it's much colder, but it's also much thinner. And so that's going to change the way sound, the speed of sound is actually slower on Mars because of that. But there's something else. In addition to that, our atmosphere is primarily nitrogen, and Mars' atmosphere is primarily carbon dioxide. So those molecules are a little bit different, and they affect sound and the propagation of sound differently. And one thing about Mars is a lot of the high sounds will sort of get clipped out on Mars. So that means like your dog whistle wouldn't really work on Mars. So dogs really aren't going to have an advantage of better hearing on Mars one day when there are dogs on Mars. So, but things would sound just a little bit different. So if you were to sort of, you can kind of imagine when we do this test that I'm going to play in a minute for a little sound clip I recorded, and then have a version of it that you would, what it would sound like on Mars. You can think if you were able to hold your breath and open up your helmet on Mars, of course you'd have to do that because you can't breathe and it'd be really cold. But and you tried to speak to somebody next to you, it would sound differently. It would not sound like it would if you were in like an Earth-type atmosphere. So let's try to listen to these sounds. I'm going to play first. This is me on Earth. Um, so listen, you can listen to this. Hello, we're talking Mars here at Coastal Carolina University. Okay, it's about a 5-second clip. Let me give it to you one more time here on Earth. Hello, we're talking Mars here at Coastal Carolina University. Now this exact same thing on Mars would sound like this. Hello, we're talking Mars here at Coastal Carolina University. We'll do this one more time. Hello, we're talking Mars here at Coastal Carolina University. So the interesting thing is it almost sounds like you're getting a bit smothered, but you aren't. It wouldn't matter how loud you talk, it would still sound incorrect to human ears. It still sound like it kind of muffled, even though even if you said it very, very loud. So it would be something you'd have to get used to if you were able to talk inside, if you were able to survive in the Martian atmosphere. So one of the things that came out this week, and I know we're almost out of time, is that they actually NASA released the first recording ever done on Mars. So I'm going to go ahead and play that. It's about 18 seconds long, and the first maybe 5 seconds is really super quiet, so you may not hear anything, but then you actually hear the wind blowing on Mars. And this is actually cool because it's the first time we've ever recorded sound on another planet. So I'm going to go ahead and play that now. Okay, hopefully you heard that. Let's see, I'll play it one more time. That is the sound of the wind on Mars, and that's really incredible. It's the first time we've ever heard it. That's actually a filtered version because the rover actually makes noise. So if I play one, I'll play one with the Rover noise embedded. It's the exact same clip, exact same length, but you'll hear like the little whine of the Rover. So if you were standing next to the Rover on Mars, this is kind of what you'd hear. So you can kind of hear the little whine in the background. So that's the news from this week on Mars. Check out the website where you can listen to both. You can listen to these audio clips, and you can also record your own greetings and listen to what things would sound like, and read a few more details about the Mars atmosphere. So hopefully you enjoyed this week's presentation, and we'll talk to everybody next week. Thanks.